We're now going to start the next chapter, which is on pressure measurement. So first, we need to understand what is pressure. So typically, when we say pressure, we are referring to fluid pressure here. And pressure is typically defined as force exerted by a fluid per unit area. Let's say you take some fluid in a container and you pick a very small area of cross section here, and if the distance in the vertical direction is x and area of cross section is a, you can always say that the weight of this fluid is basically density times volume times gravity, right? So density times volume is area of cross section times x into gravity. That if you divide by the cross sectional area, so the area get cancelled. So you will only have rho into g into x, right? So that is basically pressure, hydrostatic pressure at a particular x, right? So that satisfies force exerted by a fluid per unit area. Okay, but so that works fine for solid and in fluid in certain scenario. But in fluid, the thing is, if you change the area of the bottom surface, still the pressure is remaining the same. That means the pressure is only a function of height of the liquid column. Let's say I make this container area tapered, right? Maybe something like this, let's say. Now the weight of the water is changing. That means the force per unit area will change, but the pressure remains the same because pressure is only a function of the height of the liquid column. So to illustrate this, we have three examples here. So in one case, so we have a perfect, rectangular cross section. Here we have a trapezoidal cross section where the bottom area is reduced, okay, smaller than this area. In another case, the bottom area is increased, okay, larger than this bottom area. So in all three cases, since the height of the liquid is same, the pressure is going to be the same. But if you go by this definition that it is force exerted by fluid per unit area, this is going to be different. So really, this definition, although it works fine for solid, it doesn't really work for liquid. Now here is the catch, right? If you say my force is weight of the fluid divided by the cross-sectional area, then where the extra force is going? So in case of a vertical side walls, whatever force comes from the weight of the liquid is balanced by the upward force, and which is basically the pressure. Consequence of that is pressure. If you do a free body diagram, the weight is balanced by the reaction force, and this reaction force is basically P into A, right? Pressure into the area of cross section here will be equal to the mass of the liquid times the gravity. But when you make this, sort of the area smaller with this slanted walls slanting inward, then you would see that this force balance is not satisfied at the bottom surface. But if you do a free body diagram of this fluid element, there is some reaction force coming from the wall. And this reaction force has a vertical component, right? So now the vertical component of the reaction force on the side walls plus this upward force would equate mass times gravity. Okay, so this is how the force balance is ensured here, because mechanics should work. This force balance is ensured, but this force balance is coming from the side walls. Similarly, if you have a outward slanted wall, side walls, the reaction force will have a component in the downward direction. So in this case, this F up will be equal to M3 into G plus the reaction force in the side wall. So that is how, if you change the shape of the container, although the free body diagram of the fluid element, the bulk fluid element is ensured, the pressure at the bottom will only be a function of the height of the liquid column. Okay. Now let us try to understand different units of pressure. Okay, so pressure is really, very important in many industrial and day-to-day life applications. So we need to know, what are the different units in which pressure is expressed. The most common units of pressure is Pascal, and Pascal is also known as Newton per meter square. This is the SI unit of pressure. Sometimes we talk about, atmospheric pressure, right? My pressure is 2 atmospheric, 3 atmospheric, 10 atmospheric. What does it really mean? 1 atmospheric pressure corresponds to 760 millimeter of mercury column, right? So that means density of the mercury times 0.76 into the G, which is acceleration due to gravity, gives you 1 atmospheric pressure. And one atmospheric pressure is also 1.013 into 10 to the 5 Pascal, which is also 10.3 millimeter of water, or in terms of inch of mercury column, 29.9 inch of mercury. So there are different ways you can represent 1 atmospheric pressure. 1 mm of mercury column, that means density of mercury, which is 13.6 into 10 to the 3 kg per meter cube, into acceleration due to gravity, G, into 1 mm, that is 10 to the minus 3, that pressure is 1 torr of pressure. Now, this is another unit of pressure, 1 torr. Typically, vacuum pressure is noted in terms of torr, T-O-R-R. So, as we said, 1 torr is 1 mm by G, but this is also equal to 1.316 10 to the minus 3 atmospheric pressure, or 133.3 Pascal, right? All these units are interchangeable. You don't have to remember, just remember 1 unit and how they convert with each other, and then you should be fine. 1 bar is another unit of pressure. 1 bar is basically approximately 1 atmosphere. Here we say, right, 1 atmosphere is approximately 10 to the 5 Pascal, which is 1 bar of pressure. If somebody asks you 1 millimeter height of water, what is the pressure that corresponds? What is the pressure at the bottom of that container that contains 1 mm of water? This will be nearly equal to 10 Pascal. Okay. And there is also another unit of pressure, which is PSI, basically pound per square inch. And 1 PSI is 6.894 kilopascal. Okay. So, I mean, these are more or less almost, entire range of units that are used for pressure, which are presented here. So you can convert back and forth and convert 1 unit into another and so on. Right. So what is the source of pressure? The source of pressure is basically the kinetic energy of the molecules. And it is basically because of the momentum exchange between the molecules of the fluid and the container wall. So this you can understand from the kinetic theory of gases. The total momentum exchange would depend on the total number of molecules that are striking the wall per unit time, right? Because if you have the same volume and you have higher pressure, that means you have more number of molecules, right? So they would exert more pressure, right? And the average striking velocity also influence the pressure. If the temperature is high, for example, the molecules will move faster. They will bombard the wall at a higher velocity. So your pressure is going to be higher. From kinetic theory of gases, you can represent pressure as 1/3 of the number density of molecules. That means number of molecules per unit volume times the molecular mass of the fluid molecule into the square of the RMS velocity. Okay, this is how you can express pressure technically. And this RMS velocity can be obtained from thermal energy, which is Boltzmann constant times temperature. And this is typically expressed as 3 times Boltzmann constant temperature divided by m square root. And in that context, you can talk about mean free path. Mean free path is basically the average distance that a molecule of a fluid travels between two successive collisions. And this is typically expressed in this form. The lambda, which is the mean free path, is given as square root of 2 divided by 8 pi r square into n. R is the radius of the molecule, and n is the number density. And for air, it can be expressed in terms of temperature and pressure. So for air, lambda is expressed as 8.6 per 10⁻⁷ temperature over pressure, T by P, fit, or 2.27 10⁻⁵ T over P meter. So this is from the kinetic theory of gases, how the molecules will interact with each other, they will collide with each other over this mean free path, and how you can express pressure in terms of this RMS velocity, number density, and molecular mass. Now, it is important to understand these different terminologies with respect to pressure. So here, the bottommost horizontal axis represent absolute zero pressure. Absolute zero pressure is when the temperature is minus 273 Kelvin. This is where the molecules cease to move. And if you have some fluid in a container and your temperature is minus 273 Kelvin, the fluid will have no pressure. Okay, zero absolute pressure. Now, this line, this horizontal line, represents atmospheric pressure, that is typically 10⁵ Pascal. Any pressure above atmospheric pressure is known as positive gas pressure, which is the difference between the total or absolute pressure minus the atmospheric pressure. Okay. And any pressure which is below the atmospheric pressure is known as negative gas pressure, or it is also known as vacuum pressure, right? And in this case, the total or absolute pressure plus the gas pressure will give you the atmospheric pressure, right? Now, the different instruments that can be used for measuring pressure that we are going to talk about. You can use, this is called the pitot tube, okay, and this is known as the manometer tube, and here you basically, you insert into the tube the pipe in which the fluid is flowing by just creating a hole. And this would basically give you the static pressure, okay. This arrangement will give you the static pressure. And if you use the pitot static tube, it will not only give you the static pressure, it will also give you the dynamic pressure, right? So P over rho G is basically the static pressure which is given by this pitot tube. But if you use a pitot static tube, what happens is here, the fluid molecules come to rest. So the kinetic energy that is there in the fluid molecule before coming to this point will be converted to an equivalent pressure head, okay, which is known as the kinetic pressure head, that is expressed as V square divided by 2G. So this kind of arrangement, a static tube arrangement, will give you the static plus dynamic pressure, which is known as stagnation pressure. So we're going to look at these things in detail. But you can also have something like this, which is known as U-tube manometer. And depending on the pressure difference between the two limbs of the U-tube manometer, you can have a differential height, H. And if you know the density of this manometer, the rho times G times the differential height will give you the differential pressure. Okay. So we'll talk about various types of instrument in this chapter. So these are the things that we're going to cover. So basically these pressure sensors are classified based on the working principles. The first kind of method that we're going to look at are basically based on the balance of pressure by liquid column or some kind of dead weight. So in this category, we're going to look at dead weight tester, piezometer, manometer, micromanometer, McLeod gauge. And pressure can also be measured by looking at the elastic deformation caused by pressure. In this category, we're going to look at Bourdon tube, elastic diaphragm, bellows, and deformation of specially shaped tubes. Then there are special methods that we're going to look at: conductivity gauge, ionization gauge, Knudsen gauge, Bridgman gauge, and so on. And we'll briefly talk about some micropressure sensors. Okay. So now the first thing is the deadweight tester. Deadweight tester is typically used for calibrating pressure gauge. Okay, let's say you have a pressure gauge here, which you want to calibrate. So what you do typically is you have an arrangement which looks something like this. So you have a piston, cylinder, and the chamber arrangement here. Okay, so this is the chamber. And in one limb of the chamber is connected to a plunger, which is movable. There is a screw, lead screw kind of arrangement here, which can be moved up and down in this direction. And here you have a cylinder kind of arrangement at the top, and you have a piston. And this piston is connected to a platform on which you can keep some standard weight. And here you create a fluid line and connect to a pressure gauge that you want to calibrate. Okay. So what you do is basically first you apply some kind of pressure by applying some kind of weight at the top of this platform. So if you know the weight, you can calculate the pressure here. So basically P into the area of cross section here will be basically the weight of the standard weight times the friction force, which is acting downward, because this pressure would try to push it up. So the standard weight plus the friction force is acting downward. So from this force balance, you can actually find out. So from knowing the standard weight M into G plus the frictional force, you theoretically calculate the pressure. Now you have a pressure gauge here. So you read the pressure that is read by the pressure gauge. Now the pressure read by the pressure gauge and the pressure calculated theoretically by knowing the standard weight has to match. Okay, so that way you can actually calibrate the pressure gauge, right?
Sir, this type of equipment is used in which application, sir?
So I said when you want to calibrate a pressure transducer, right?
Oh,
so
okay.
you have
Only
a
for
calibration
calibration purpose.
dial gauge, and so you can calibrate because from the standard weight you can know the pressure, right, using this formula. And
Right.
if you know this pressure, and if this dial gauge is not showing that pressure, that means it is calibrated. Okay, so you need to really calibrate this to match to this pressure.
Right. Thank you.
Right. So now this is called the piezometer. And here basically you have a tube through which some fluid is flowing. Okay. And you want to measure the pressure inside. So you create a small hole here and you insert a tube. When you insert a tube, depending on the pressure here, the liquid will rise up, right? And the liquid will stop rising when the hydrostatic pressure, because of this liquid column, would equate with the actual pressure here inside the tube at this point. Okay. So you can write that pressure here is nothing but the atmospheric pressure plus the hydrostatic pressure, which is rho g into H. Okay. And this method you can use for liquid, because liquid is, there will be a clear meniscus and you can read what is the height as compared to the center line of the tube here. And you can predict the pressure. But this cannot be used for gases, because gases, unlike liquid, will escape. So you won't see an interface. So this method cannot be applicable to gases. Other limitation of this kind of instrument is that if the pressure is below atmospheric here, for liquid, the liquid will not rise, right? So this method cannot be used for subatmospheric pressure measurement. Okay. So typically, this kind of arrangement is used, for application where your pressure is within the range of 0.1 mm of mercury to about 10 to the power 4 mm of mercury. The second kind of pressure measuring instrument that you use is known as U-tube manometer. Okay, so this is typically a U-tube manometer, and typically you use some kind of a working fluid. The most commonly used working fluids are water and mercury. What you do is you fill this manometer with water or mercury, and initially both these limbs are open to atmosphere. So it will have the same level on the right and left. Now one of the limb you expose to a pressure source. Okay. Now if this pressure P is different from the atmospheric pressure, depending on whether P is greater than PA or P is less than PA, you see that this level on the left and right will be different, right? So in this case, let's say P is greater than PA. So the liquid level in the left will go down and liquid level in the right will go up. Okay, let's say initially both these levels were somewhere here, right? And since this pressure is greater than atmospheric pressure, the level here has gone down and the level here has gone up. Now you need to measure the height difference between the left limb and right limb, the liquid meniscus levels, right? Let this be H. So you can write down that this pressure P plus the rho of this fluid, right? Because you are measuring pressure of some fluid. That fluid has filled now here. So rho of fluid times G into H, that is the pressure at this level. And that should be equal to the atmospheric pressure is here plus the manometric liquid. The manometric liquid and the source liquid have to be different. Okay, then only you will see an interface between them. Okay, if you are using water as the manometric liquid, if you're trying to measure pressure of a container or a tube where water is flowing, then you won't see any meniscus, right? So the manometric liquid and the source fluid have to be different. So now, so this is density of the manometric liquid, G into H. So again, you are measuring pressure at this level. So they have to be equal. And from here, you can know the excess pressure. That means the source pressure minus the atmospheric pressure is basically the manometric liquid density minus the source fluid liquid into G into H. Okay. So the manometer liquid is chosen based on the density and pressure to be measured. Okay. If you are measuring, a small pressure difference between the source pressure and the atmospheric pressure, that means your P minus PA is, very small. That means your H will be very small, right? And if the if you want to have a significant pressure difference, you need to use a high density fluid here. Okay, the manometric liquid. Sorry, if you are using a large pressure difference, P minus PA is very high. Unless you use rho m minus rho f is very high, your H will shoot up, right? Now your H, there will be a limit because the manometric fluid should not come out of it. So that means there will be a definite maximum H will have a limit H max. So if P minus PA is very high, that means your rho m minus rho f have to be very high. Okay, that means you must choose a manometric liquid which is much denser than the source liquid. On the other extreme, if you are trying to measure a very low pressure, okay, and when you have a very low pressure, the H should be significant enough for you to measure. Okay, so H will be significant in the low pressure limit when rho m minus rho f is small. That means you must choose a manometric liquid whose density is marginally greater than the source fluid density. So depending on what is the pressure difference that is expected, you have to appropriately choose the manometric liquid as compared to the source fluid. Now, what should be the characteristics of a manometric liquid? It should have low viscosity, because let's say the source pressure is changing frequently. If the viscosity of the manometric liquid is very high, it will take a long time to actually settle down, because the resistance offered by the tube will be very large, and the time constant of the system would increase proportional to viscosity, as you would see when you do a second order analysis of manometer system, okay, which we'll be doing soon. So we need a low viscosity for quick level adjustment, negligible surface tension and capillarity effect. So if the surface tension or capillarity effect is very strong, then this liquid will not stabilize easily, okay, for a pressure change, and the curvature will be very strong, and that makes measurement difficult. Also, the liquid should have minimum density change with temperature. Suddenly, let's say you are measuring, you have calibrated this in winter, and then you are measuring in summer, there is a temperature difference. The manometer liquid density is a function of temperature, then you have to do recalibration. And if you want to avoid that, you need to pick a liquid whose density is not sensitive to temperature. And the liquid should be non-corrosive, so that you can do a pressure measurement over extended period of time. This U2 manometer, several modifications are possible to improve its sensitivity and usability and so on. And this is what we are going to talk about subsequently. You can have a cistern or well in one of the limbs, okay, so that you need not really look at the height difference. You can just look at what is the level in one of the limbs, and you will be done with it. And you can improve sensitivity by making one limb inclined. So we'll also see an inclined U2 manometer where one of the limbs will be not straight vertical, it will be inclined to improve the sensitivity. And you can also improve sensitivity by using low density fluid. That means if the rho m is small, that means this difference is small, H will be very large. So the sensitivity can be improved by picking a manometric liquid having low density. And as we discussed, high pressure requires high density fluid. If P minus P is very high, you must pick rho m to be very high so that H is limited. Otherwise, the manometric fluid will overflow. And the capillary meniscus error is minimized by fixing a reference point. So what means is that line, because depending on the material of the capillary, typically the meniscus will be curved because the liquid tend to wet the liquid surface. Now, when you measure this height difference, where do you look at? Do you look at here or do you look at the bottom? So you must pick a reference point. Maybe just the center of the bottommost point of the meniscus you take as a reference point here, and as well as here to here to know the height difference. So the reference points needs to be fixed. Now, this is a modification of U-tube manometer, which is called well-type manometer. Okay, so what is the benefit of well-type manometer? The benefit is that we need not really look at the level on the left. We can just read the level on the right. Okay, the height in the right. We need not worry about the level in the left. So how it is? So you have a large chamber on the left. So when there is a pressure change, when P is different compared to P atmospheric, on the, let's say P is higher than P atmospheric. On the left, the meniscus is going to go down, the level is going to go down. On the right, it is going to go up. But this is the same volume of fluid that is, going down here will go up here. But this chamber has a area of cross-section much larger than that in the right limb. So if you equate the volume that is coming down here, that is, the volume of liquid that is moving down here will be same as the volume of liquid moving up here. So H dash is, let's say, the volume, the height that is the liquid level height that is going down. A is the area of cross-section of this reservoir or well. So H dash into A will be the height H by which it will rise in the right side into the area of cross-section. Now this small a is much smaller than the capital A, right? So anyway, we'll talk about that soon. Then you do a force balance, the pressure balance. So pressure here, P, plus density of the source fluid into G into H plus H dash will be equal to the atmospheric pressure PA plus manometric liquid rho mg into H plus H dash. So you're basically equating the pressure at this level. Okay. So your P minus PA is going to be rho m minus rho f into G into 1 plus A over A into H. And now, if you say this small area of cross-section is much smaller than the large area of cross-section, you can neglect this term. So you can just simply say that P minus PA is rho m minus rho f into G into H. Okay. That means you don't need to really look at what is happening in the left limb. The height by which the liquid is going to rise in the right limb only needs to be monitored. Okay. So that basically helps that you don't need to really look at the left and right and so on. Just by looking at one of the limbs, you can, and if you have a scale, it makes it a lot easier. Just look at one limb and find out the height difference. And in fact, you may incur a very small amount of error by neglecting this term. And if you have a scale on the right limb, that can also accommodate this error, small error you may incur. Okay. And here you can achieve higher sensitivity because for a small change in P, you can, because this area of cross-section is large, you can have a large, because the area of cross-section is large, so P into A is going to be large, right? And so that is why you can get a appreciable edge here, which can improve the sensitivity of this manometer. The other way you can improve the sensitivity is by making the right limb inclined. When you make the right limb inclined, so this is the balance that we had. H dash into A is H into A. Now in this case, your H is basically along the tube, which we call it as R. But here, the manometer height can be expressed as your, if this is R, this height is going to be R sine theta. Okay. So in this case, this H that we have here becomes R sine theta. So you have R into sine theta into A by A. Okay. So P minus PA will be rho M minus rho F into G into sine theta A by A into the R. R is along the length. So you can compare, let's say, if theta is 30 degree, then for a given change in pressure, if it is H, that will get amplified into a much larger distance here along the length of the inclined tube. So instead of H, it will become 2H because theta is 30 degree. So you have basically R sine theta equal to H. So R will be equal to H by sine theta. So sine 30 is half. So it will become 2H, right? So for the same change in pressure, your length of the liquid column along the tube is doubled. Okay. So that means as compared to here H, if you make it inclined at 30 degree, this length along the inclined tube will be twice H. So that way, for a small change in pressure, the liquid will rise over a longer distance. That means you are able to measure it much better. That means your sensitivity is increasing. Right. So this is called micro manometer. This is a way of measuring the height difference. One way to measure the height difference is look at this label here. Just using your eye over a scale and try to look at the same on the right side and try to find the height difference manually. You can improve this by using manometers, micrometers, basically arranged in both these limbs. And these micrometers will have a scale in there. So you can precisely read by how much you have to move this micrometer head down to, initially they will be at some same height, right? When there is a pressure difference, let's say P2 is greater than P1, this side the level will go down, this side the level will go up, which will create a height difference. Now, initially your tip will be touching the native interface. Let's say the native interface was somewhere here. So now the tip would move from this location to this location. So you can precisely measure by how much you have to move the micrometer head down. This micrometer head will move up, right? Initially it was here, now it has to move here. So it has moved up. So you can again precisely measure here how much it has moved up. So there you can have a better measurement, right? Instead of relying on the level by your eye, you have a mechanical arrangement to actually measure the height difference. In fact, in some systems, you can automate it. That means you can sort of measure this change in the height by measuring the capacitance change, for example. Let's say you have things like an linear variable differential transformer, LVDT kind of thing to measure the displacement that this thing has to go up and this thing has to go down and this thing has to go up. So you can also measure either mechanically by looking at the scale or by electrically. Okay, so there is some special arrangement to read the height level very accurately when that becomes critical. This is again another arrangement where you can measure the the height difference more accurately using a single micrometer and a flexible tubing arrangement. So typically, you have one end of the limb connected to this chamber here, and another end of, here, this is, let's say, connected to a source pressure, whose pressure you want to measure. Initially, both will be at P1, and when you expose this to the source, this pressure becomes P2. So for this pressure difference, let's say if this pressure is higher, what will happen is, now this is basically a flexible tube. Okay. Now, what will happen is, when the pressure changes, your levels are now going to be different, right? So here, for example, if this pressure is higher, this meniscus will move down, right? When this meniscus moves down, one way to look at is, the height difference between left and right, but you don't want to do that. That may involve error. So what you do is, now you use this micrometer to move this platform up or down. You move this platform up or down to, let's say this is the displaced position because of the higher pressure, the meniscus has come here. You move this up and down to take this meniscus back to this crosshair. Okay, initially this is at crosshair, the level is here, both pressures are same. Now this pressure difference is higher, so this meniscus, liquid meniscus, goes down, and then you basically move this thing up and down to basically bring this level back to here. Okay, so that way you would know by how much you had to move this platform up and down, which is related to this pressure. Okay. The other instrument that we are going to talk about now is known as McLeod gauge. McLeod gauges are used typically for measuring vacuum pressure, subatmospheric pressure. And this can measure very low pressure up to about 10 to the power minus 4 torr of pressure. How does it work? So you have this arrangement of the McLeod gauge. So let's say here you use mercury as the working fluid. This is connected to the source pressure, and the source is at a subatmospheric pressure or a vacuum pressure. Okay. What you do is, so this is basically fluidically connected to this chamber, and there is a plunger. So you initially, this plunger is moved off. It is moved off until the entire liquid, the mercury here, comes to this level. Okay, everything here, the entire mercury empties and comes to this level, right? So here it is basically occupied by the source fluid, which is at a negative pressure. So everything becomes white. The mercury, which is by the dashed line, goes down and fills something here. Now, what is of importance is the volume of this volume V, which is from this point to this point. So this amount of fluid, which is at negative pressure, is basically trapped. How you can trap this? So you move this plunger down. When you move this plunger down, then this amount of the source fluid is trapped. Okay, so the mercury basically goes up here and fills everywhere. It also tries to go up. Essentially, the fluid, which was initially at negative pressure in this volume, gets compressed by this rising mercury to this small volume here. Okay. So you can apply Boyle's law, which is basically PV equal to constant. So initially, the pressure of this source fluid, which is indicated by the white color, at a pressure Pi, that is something that you want to measure. And the volume of this region here is basically V. And that is now compressed to this small volume, which is basically the pressure now here, compressed pressure P, into the area of cross section of this tube A, into the height of this source fluid, right? The transparent fluid here, P into A into H. Now this P you can find by comparing the level and level here, because here the pressure is Pi, and here this pressure P would be basically Pi plus the height of this here into rho into G. That is the specific gravity, okay, density of this mercury into G. Now, if you use these two equations, instead of P here, you substitute Pi into Pi plus H gamma, and you simplify, you can show that this source pressure Pi is basically given as gamma AH square divided by V minus AH. So you can predict what was the source pressure, what is the source pressure, just by measuring this height difference between this mercury meniscus here and this mercury meniscus on this limb H. Because everything else is geometrical parameter. A is the geometric area of cross section of this tube, V is the volume of this tube here, and gamma is basically the property of the manometer, the liquid that is used here, which is mercury. So with this geometrical parameter and the mercury, the working fluid density, you can, and measuring the H, you can predict what is Pi. Now, if you say that this volume here is much greater than this compressed volume of the working fluid, that means V is greater than A into H, you can actually simplify this. If V is greater than AH, so you can just neglect AH here. So you can write that Pi over gamma is simply AH square over V. Okay. So this is how the McLeod gauge work. Okay. But there are limitations of McLeod gauge. If the source pressure is constant, then you can just move this plunger up and trap this source fluid, and you can bring it back, compress it, and note the height difference and measure pressure. But if the source pressure is dynamically changing, every time the pressure changes, you have to do this, right? And it takes finite amount of time. Okay. So you cannot really continuously do measurement. If the source pressure is changing frequently, it becomes very difficult to measure. The second problem that happens is that when you trap this fluid, which is at a negative pressure, and you compress, let's say if it is gas, there is a problem of condensation, because this is at initially at vacuum pressure, and now you are compressing this, so you may have condensation here. Okay, so once you have condensation, and next round, if you want to do measure pressure, then the condensed liquid now will basically fall off, and that will create a lot of problem in the measurement. So this is another limitation of this. Right. I just want to know the times. Give me a second. Okay, so I will stop here. If you have any question, let us discuss.
Sir Prem here. Am I audible?
Yeah, just give me 1 second.
Recording stopped.
Yeah, please go ahead.
So, can you explain a little bit about this pitot tube?
Which one you want to talk about?
Pitot tube, not specifically on the slides per se, but general working of the pitot tube and its principles.
So basically, this pitot static tube is, as I said, it measures the stagnation pressure. Okay. So you have the fluid which is flowing, and typically these fluids become stationary right at the tip of this tube, converting all the energy, kinetic energy, into pressure energy, right? So basically, this height of the liquid here would indicate not only the static pressure but also stagnation pressure. Whereas the pitot tube would basically give you the static pressure. So in fact, the difference between the stagnation pressure and the static pressure will help you measuring velocity. Okay, so this about pitot tube will learn a lot when we talk about velocity measurement. Okay, so now our objective is pressure measurement, but when we discuss velocity measurement in subsequent classes, we will talk about the construction of pitot tube, pitot static tube in detail. Okay, so but for now,
Yes,
let's focus on only pressure measurement.
okay, okay, got it. So the fluid can be anything, right? Meaning
Yeah,
the
so
one that
fluid, you have to make sure that if it is gas, then there is a problem because the fluid will escape, right?
So, sir, what I wanted to understand was the reason why I asked this question is in Formula One cars and during its testing and validation period, what I'm able to see in some videos is they are able to use some apparatus in the front wing of the car, and it is
Yes.
basically a pitot tube based arrangement, which
Mm.
says that this is the air pressure at which the front wing is going to be attacked by the air,
Yes.
and you have to design the wing position and everything like that. And the aerodynamics is studied that way, right?
Yes.
So the point that is going to be exposed to the wind or the air will be the one where you're indicating the arrow mark, right?
Yes. So in that
And the
case, what
torque,
you use is basically the pitot tube. If it is air, so this manometric liquid now. So basically, this is now connected to this one limb of the U-tube manometer. So this you can use this water. Okay, and this is again
that
open.
way they'll have a closed loop then.
Yes,
Okay.
so that way there is they won't mix with each other.
And the rise in the levels would be measured by some indicating some
Some high difference, that you can measure.
Yeah. Okay. Got it, sir. Yeah, thank you.
Hello. Hello. Hello, sir.
Anybody else has any other question?
Someone is talking, but the voice is not audible.
Hello.
Yeah.
Yeah, sir. Suppose in the manometer we have two different fluids with two different densities, and they have different behaviors in terms of meniscus. One has a upper meniscus and the other has lower meniscus in either ends. Then how is it determined which meniscus is to be considered there, sir?
I did not understand the question. Can you say it again?
Sir, suppose in the manometer we have two different fluids.
Okay, so the working fluid, you don't have only one fluid, you have two different fluids.
Yes, and the densities are different, and because
Yeah.
of the change in
Yeah,
density, we
I
have
got it.
different
I got it. So basically, now it is become a composite manometer system. Okay. So there you have to consider basically, but still the pressure balance should still hold true. Let's say you have one more liquid here. So you depending whenever you have a pressure difference, now it becomes a stark system. So you say rho one into G into H1 plus rho two into G into H2 should be equal to again. So basically, you come from one side to a particular. See, what is important is you draw a horizontal line, and at that horizontal line, you come from the left from the source pressure and come to this level. And the right hand side also, you start from the atmospheric pressure and come to this level. It doesn't matter how many liquids you have. You just have to, say rho 1 into G into H1, rho 2 into G into H2, and so on and so forth. Okay.
And what about the meniscus, sir? Suppose fluid 1 has lower meniscus and the fluid 2 has upper meniscus. So that
I didn't understand what exactly you mean by lower meniscus and upper meniscus.
in the sense, in one fluid we have the normal U kind of meniscus, sir.
Oh,
the
okay. You are saying the weighting properties are very different, right? Something you have a curved and something you have straight,
Yes.
right? So, I mean, as you said, what is important is the reference point. So, one way they say is that if you have a curved meniscus, both in left limb and right limb, you take the center lowest point. Okay, let's say something else, some other fluid, you are using multiple fluid and something has some meniscus, which is, let's say something like that, right? So both in the left limb and the right limb, you fix the reference point. It could be the lowest point or the highest point. If you fix the reference point, then it doesn't matter really whether, how many fluids you have, and independent of their properties, you would be able to balance. Because eventually it is basically pressure head balance. You draw horizontal line here or here, it doesn't matter. You start from this pressure, go by all these stacked layers to this, okay. Hydrostatic pressure is ρ1, G1, H1. Here also you go from atmospheric pressure to that level. And you fix your reference point. Could be bottom of the meniscus on both sides, irrespective of whether this curvature is flat, this curvature is more U, it doesn't really. But be
Understood.
consistent, whatever you are doing, whatever reference point here, and the same reference point should be on the right hand side. Okay.
Okay.
Sir, one doubt. So,
Yeah.
should the working fluid always have higher density than the measured fluid, or there is no?
See the when you have a vacuum pressure, right? So P will be less than PA, right? So this will be negative. So that means it will be advisable for the H to be positive. You can even use ρf less than ρm. So basically, whether H is off here or H is off here, you can decide to use ρm and ρf. But the problem is if ρm is, this is less dense and this is highly dense, there is going to be a buoyancy issue. Okay, low density fluid always tend to rise, so that issue is always there. So it will really depend on the kind of system that you have. Okay, and depending on that, you should take a decision. I mean, the orientation of the U-tube and so on. Like if you put the U-tube like this, you have to make sure that this low density fluid doesn't rise. But if you flip it to 180 degree, then you can use this as a low density and this as a high density. Okay. So I mean, it depends on the orientation, depends on the pressure and so on. Okay. There is no unique answer to your question.
Okay, sir. Thank you.
Thank you, sir.
Okay, thank you. And yeah, we'll meet next week. And you can drop me an email. I will share some questions on temperature.
Sure, sir. Sure. Thank you, sir. Thank you, sir.
Thank you.
Thank you.
Thank you, sir.